structural determination. This is a structural determination by X-ray crystallography, in which the incident X-ray should be scattered at three different planes. That is plane number 0, plane number 4. That is first phase, second phase, and third phase. This is the uh, density of an density distribution in the different lattice plane. That is HKL. So this is the normal structure of uh, X-ray crystallography. So this is a description of the plane. This is a plane in which the point P can be described by the vector which is perpendicular to the plane, that is L, M and N. So we will use the L, N and N plane in which the coordinate X, Y, Z. So interpret equation of the interpret intercept equation of the plane is given by X by A, Y by B, then Z by C. This can be arranged in the X cos, S cos, gamma plus y cos phi and z cos omega. This is the parallel plane in which they locate the distance at different angles. So this is the theta theta p equal to p by cos lambda, p by cos lambda, then bp equal to p by cos pi, then cp equal to p by cos omega. So this is the part difference. Part difference, you know that from previous previous plan in which the part difference you have to see that x cos pi plus y cos s cos lambda plus y cos pi plus z cos omega equal to p. That is the part difference. So for a plane O, p equal to qhl, a equal to a by h, b equal to b by k, c equal to cl. That is cos lambda is equal to, this is the equation we get from the plane A, PA equal to DA, that is atom XA, XY and ZA. That is from this we can calculate from the plane O. So we got the equation from the using fresh fractional coordinate. According to the Bragg's law, the part difference between O and A is, you know very well about Bragg's law. Lambda equal to 2d sine theta. This is the sine theta which can be mentioned has a different part difference. So this is the delta A equal to lambda hxa plus kya plus zka. This is using the wave equation. Instead of, we can use the w naught equal to f cos theta 2 pi x divided by lambda, or w naught is equal to f cos omega t, where v naught is w naught is the transverse displacement of a wave moving in a x direction. The maximum amplitude is f at t is equal to 0 and x is equal to 0. For other wave with a maximum at t equal to Tn, x is equal to xn, we can write Wn is equal to f. From this equation we can calculate this. From after calculating the Wn, we get a two arbitrary wave of the same frequency. This is a two arbitrary wave at the same frequency. Look at that, the equation should be a similarly same from the pi 1 and pi 2. So sum equal to w is equal to sum w is equal to v1 w1 plus w2. After getting both equation add, we can get this equation. From that we can calculate the w at any wave. So we know that we can write any wave, w is equal to f cos theta f omega t minus pi equal to f cos omega t cos pi plus sin omega t. This is a wave equation in which we can compare the previous slide in which the equation should be common. So from f can be calculated from this equation. After calculating, f is equal to f1 cos theta pi 1 plus f2 cos theta pi 2 whole square plus f1 sin theta pi 1 plus f2 sin pi 2 whole square whole power 1 by 2. After comparing the equation, from this we get a Argand equation. There is a crystal structural analysis from the different real and imaginary component at the f is equal to f dot cos alpha t plus I sin alpha t equal to f of e power I alpha t. Similarly, the Argand equation at degree alpha is equal to 0 degree, alpha is equal to 90 degree, alpha equal to 45 degree, alpha is equal to 25 degrees. This is a similar angle at different amplitude we have to see in the Argand equation. From this we can add the different alter any number of waves can be added using the Argand wave. For n wave is equal to f cos phi equal to sigma f of j cos j, f sin phi equal to summation over j is equal to 1 and n fj sin phi fj sin phi j. So alternate we can write this equation from the determination of crystallography at different angle. You have to see in the combination of two wave and combination of en wave. So similarly, the part difference from our treatment of part difference of wave scattered by an arbitrary atom, we obtain lambda a is equal to this equation we have to see in the atom from lattice. So this is the part difference between, so this is the phase difference can be written as pi of j is equal to 2 pi lambda into del j, which is equal to 2 pi hxj plus kyj plus ljz. This implies that our expression for f depends on the diffraction direction as described by the Miller indices HKL. So from this we can move to the next topic that is called as a structure factor. F is called as a Fourier. Fourier should be a more properly written as F is equal to HKL or FHKL to express it depends on the diffraction. There will be a unique corresponding to each reflection. So this is a all atoms should be a contribute from the HL plane at the HL. This is a F HKL indices is called as a structural factor. So the we can broke the real and imaginary part. We get this equation. From this we can calculate the different A and a different B. So from that we can move to the another topic that is called as atomic form factor, that is called as the atomic structural factor. The individual component f of j are called atomic structural factor. This is structural factor having the different nature, direction of the scattering and X-ray wavelength. Provide a measure of how efficiency of an atom is scattered X-ray compared to an electron. Usually written as f of j, although they should be written as f of j comma theta comma lambda. From this function as sin theta by lambda for each atom in an international tables. So from that maximum value of f of j is z of j, the number of electron of the jth atom. So intensity and structural factor. This is now we shall move to the another topic that is called the intensity and structure factor. We cannot measure structure factor. Instead of we will use the measure that intensity of diffracted beam. H of HKL is proportional to F of HKL F into HKL, that is equal to F into HKL equal to mod of f of HKL e power minus I pi, that is mod of HKL whole square equal to a square plus HKL plus b square plus HKL. This equation we seen in the previous table. This is the equation in the structural factor. We will see in the same in the intensity and structural factor. The phase difference is given by the lambda pi equal to b HKL plus BHKL divided by AHKL. So in which the problem is phase transformation when the measuring intensity should be a changes. This is the changes factor between I and F. This is a several factor between I and F will changes in the measured intensity, thermal vibration of an atom, Lorentz factor, absorption, then polarization and scale factor. This is a force between factor between I and F. So similarly, the thermal vibration smear out that the electron cloud surrounding an atom, we see time average overall configuration. This is the curve will be the time average overall configuration from Fj to Zj. The point atom should be a F, the actual atom should be a different area. So displacement of an atom leads to slightly part difference for atom in neighboring unit cell. So this is the equation. So the value should be a changes in the mean square amplitude of the displacement. So similarly, the how the thermal vibration should be absence in the lattice centering, glide plane and screw axis. So similarly, this is the uh, systematic absence in the thermal vibration. So we can calculate the different condition for the unit cell, screw axis and glide phases. This is a small determination should be a changes in the limiting of unit cell, screw axis and glide plane. Similarly, now one of the most important topic is Fourier transform and its crystal. So this is the Fourier transform. This is the two component. One is the first line it shows the crystal lattice. Another the first line it shows the reciprocal lattice. Then so this is the 2 point. This is the Fourier transform. This is the Fourier transform of crystal structure. So we should be a analysis from the different relationship between crystal structure and the part difference of the Fourier transformation. So crystal lattice it involved in the crystal structure, that is sigma xyz value. Then it should be a diffraction pattern of Miller indices f of HKL value. So it should be a multiplication of the reciprocal lattice. Similarly, the unit cell content is also a convolution of the different value. After that, the value should be in the form of diffraction. So after that, it should be a multiply from the different pattern of the unit cell. It should be a changes from the molecular transform. This is the simple diagram of Fourier transform and its crystal. So from that, the Fourier transform of and its structure, the electron density in a crystal can be described as a periodic function. Same content in each unit cell represented by the sum of cosine and sine function. Because the wavelength is related to lattice periodically, the construction of periodic function by the summation of sine and cosine waves is called a Fourier synthesis. The decomposition of periodic function into a sine and cosine wave is called Fourier analysis. The summation over sine and cosine wave is called Fourier synthesis. The periodic function is called as a Fourier analysis. This is the Fourier synthesis and analysis. Look at the diagram. The Fourier after similarly normal wave at 0 to 180 degree, it should be a same at the different lattice. So from that the Fourier synthesis should be a changes. Look at this is the changes from the synthesis to analysis. This is the crystal structure at the same bonding. This is a similarity from 0 to 45 degree angle. This is a 0 to 90 degree angle in which the transformation of the synthesis and analysis should be a changes. So this is the Fourier series, the complete set of components that are necessary to describe a periodic function that is called as a Fourier series. The intensity of Bragg's reflection is related to the amplitude of an electron density wave in a crystal in HKL direction. All the Bragg's peak of the Fourier series describes the electron density of a crystal. The scattering of X-ray by the atom can be regarded as a Fourier analysis by producing the Miller indices of HKL structural factor wave. So similarly, the electron density can be determined from the diffraction pattern by the Fourier transformer. This is the equation of rho of x, y, z. This is the equation 1 by v, summation over h, summation over k, summation over l, f of mod of hkl exponential minus 2 pi I by 2 pi I hx plus ky plus lz minus pi of hkl. This is the equation of Fourier series in which the another topic that is in which another topic of the Fourier wave that is called as electron density wave. In order to obtain the electron density, we need to sum all the contributing electron density wave that is called as a Fourier synthesis. The electron density wave do not have the same frequency, that is periodically depends on HKL wavelength in the distance, that is HKL. This is the periodic wave of their representation. The difference would be at Miller index HKL in the different periodic at 30, 300, then 50, then 350, 352. This is the plane should be a three times should be a rotate in the pi direction. This is the direction should be a changes in the electron density. Similarly, the summing over electron density wave from the Bragg's reflection 100, 1, 0, 0, 200, 300 Bragg's reflection. This is the scattered wave in which the Bragg reflection should be a changer. So this is the similarity 100, 200 density wave. Look at that. After summing of the density wave equal to electron density map. This is the electron density wave from the Bragg's reflection 100, 200 and 300. After summing all three atom position, it should get the peak at the different area in which the part difference should be a changes from the electron density have amplitude and relative phases. So that depends on the atomic arrangement in a direction. When the corresponding electron density map is calculated, it should be a peak at the position corresponding to actual position. This is the summation show the different map of the summing electron density wave. From that 1D example of the Fourier synthesis. This is a 1D example of the Fourier synthesis. It should be a change from the individual term from 00 to 100. From this is the electron density is depend on the 0 degree, 180 degree, and like that different waves should be a changes. This is the effect of different crystal structure in the Fourier synthesis. This is a Fourier transformation. You know the so normal equation in mathematical term, f of x is equal to integral minus omega minus sigma to plus minus sigma plus sigma e power I 2 pi x L 2xy g of y comma x. Similarly, the g of x, this is a convolution of two Fourier transformation. After summation all those equation, we will get the minus infinity to plus infinity f of x dot g x minus x dash into gx. This is a convolution of integral which expresses the amount of overlap of one function g and is shifted over another function f. It should blend one function with another. So similarly, the relation between f and rho, that is Fourier transformation and density, electron density. We have shown that the structure factor can be described by a Fourier synthesis from the wave structured by the crystal. A diffraction pattern is a Fourier transform an object. We have also shown that the electron density can be obtained by a Fourier synthesis of an electron density wave. So inverse Fourier transform of the differential diffraction pattern is give the original object. This is the inverse Fourier transformation. Similarly, from the row of x, y, z, it should be a changes at the. This is the relationship between f and rho. So this is the Fourier transformation relationship between F and rho. So this is the distance of an atom. This is the crystal structure. So the Fourier transformer equal to scattering factor. This is the value should be a changes at different orbital, different periodic function. So the distance of the atomic center should be a changes. So diffraction from the whole of in Fourier transformation. So for diffraction from diffraction the diffraction from a single hole given by a ring pattern when what happened when the one hole should be a changes. So this is a one hole the integral vr to infinity e power I 2 pi s into r rho of r dvr. So from two holes described as a two value that is called as a, this is the equation should be extra in the ring pattern. So after two pattern should be a fringe function, it will double the amplitude of a dot a naught. So this is lead to a extension halfway in between. So this is the fringe pattern. This is the fringe pattern from one and two circular holes of 1 millimeter two holes of 1 millimeter diameter. This is a figure B shows the two holes of 1 meter 1 millimeter diameter. This is a one hole, this is a two hole. This is a diffraction pattern of the different fringe pattern. So this is a hole at the in the crystal. This is the hole scattered the light ray and electron X-ray. Imagine a crystal has a hole pattern. This is a pattern should be A, B, C, D, have a different hole has shown in the crystal. Similarly, this is the opposite approach of the diffraction pattern into electron density map. This is the resolution of your electron density map will strongly depend on how many reflection you can create it. From A, B, C, this is a C, D, E, F, G. This is a different structure in which should be a changes like that. This is a, from two holes. This is a fringe pattern. So similarly, the Fourier transform of the crystal should be a changes. From that, I have to conclude the Fourier map and different structural determination.